Perhaps the simplest example of an air standard cycle is the air standard Otto cycle. The air standard Otto cycle is composed of 4 processes, and as we go through the processes, try to make connections with the processes that happen in a 4-cycle internal combustion engine, as covered in a previous video, and picture in your mind what the piston and cylinder are doing for every process. Okay, so we start at state 1 at bottom dead center, and we compress the air in the piston isentropically from bottom dead center to top dead center. So let's think about isentropic compression. Why is it isentropic? Well, if you think back to the process form of the entropy balance, we are internally reversible, so sigma dot, or our entropy generation, is 0. And if we're doing this isentropically, then there's no change in entropy, so therefore we must be doing so adiabatically. The Q over T term must also be 0 if the other 2 terms are 0. Okay, so we've compressed isentropically. As we go along, let's draw this on PV and TV diagrams. So the first one here, we'll start at 1, compress isentropically on a line of constant entropy. So S equals a constant here. Perhaps not the best line I've drawn in my life. And that goes from 1 to 2. And so that's the PV diagram. TS diagram, we're going to compress without heat transfer, so we expect our temperature to increase, and of course our entropy will not increase. So there we go, 1 to 2. All right, second process is constant volume heat transfer to the air from an external source while the piston is at top dead center. So we've compressed, and now we hold the piston at top dead center and heat the air in the piston. So that heat transfer is going to push entropy into our air, convect entropy into our air, and we're going to do so at constant volume. So a constant line of constant volume on this TS diagram looks about like that. So we're going from 2 to 3, and V equals constant. So here I'm using capital V and lowercase v interchangeably. Of course, we have a fixed mass, so whether we want to do a P big V diagram or a P little v diagram makes no difference. Okay, from 3 to 4 we have isentropic expansion back to bottom dead center. So here we're going to again adiabatically expand back to where the piston is sitting at the very bottom of the cylinder, and this is indeed our power stroke. So, oh yeah, I forgot to fill in the PV diagram for 2 to 3. All right, so this is a constant volume heating, so we expect our pressure to go up. Oh, there we go. 2 to 3. Okay. So now we're expanding isentropically here. Isentropic expansion. All right. Okay, so my power stroke from 3 to 4. And finally, we have, while the piston is at the very bottom of the cylinder, we have constant volume heating, or cooling rather, constant volume heat rejection at bottom dead center. So our volume is going to remain constant, and our pressure is going to go down. We're going to have a decrease in entropy because, again, we're pulling heat away from our system. So we're going to drop temperature a bit and also pull away some entropy. All right, next let's look at how we analyze an Otto cycle. All right, follow along this analysis with the PV diagram and the TS diagram and the description of each process as we go through this analysis. Okay, so let's now start with the process form of our first law. of course neglecting kinetic and potential energy. So I'm going to split delta U up as m delta U. Of course, our mass stays constant throughout the cycle. So I can look at heat and work for every process in the cycle. So the work from 1 to 2 of course, from 1 to 2, remember, is isentropic compression, no heat transfer. So Q12, the way that we've labeled the processes in our cycle, is 0. Also, Q34 is 0. So work 1, 2 is going over M is going to be minus U2 minus U1. All right, so that's going to be into our system as we're compressing our gas. Don't fall into the temptation of using enthalpy in this process analysis here. So again, we're using internal energy because that's what is coming from our first law energy balance. Okay, so the work from 2 to 3 is 0 because we have a constant volume. And again, the work from 4 to 1 is 0 because we have a constant volume. But Q23 is not 0, and that's going to be equal to U3 minus U2. W34 over M is going to be equal to minus U4 minus U3. And the last term we have, Q41, which will be out as we cool our gas, U1 minus U4. Okay. Let me switch markers here. Okay, so my thermal efficiency for my cycle will be W cycle, or Qn. Nothing has changed there. So I've got two works. One will be positive, one will be negative in sign. And I've only got one process, process 2 to 3, in which I'm putting heat into my gas. So here we go. I can arrange eta as 1 minus U4 minus U1 over U3 minus U2. Okay, so again, I'm really relying on defining each state and defining the internal energy of each state to calculate the various values for heat work and ultimately efficiency. Because I have two isentropic processes in this cycle, that gives me the opportunity to use some isentropic process relations to do the cycle analysis. So I encourage you to go back and watch a previous lecture on isentropic processes where we define things like pseudo-reduced volume and how we use these to analyze isentropic processes. But we're going to use those techniques and apply them specifically to the Otto cycle now. And we're going to make use of our ideal gas table, which has these different values as a function of temperature, and use ratios of these values to calculate different things about our various states. Okay, so recall that VR2 over VR1, which both of these values come from the ideal gas table, is going to be equal to the ratio of V2 over V1. So I can say that VR2 is equal to VR1 times 1 over R, or just put that over R, and you say, oh wait, where does R come from? Remember, this is our compression ratio, which we defined in a previous lecture. R is the volume at bottom dead center over the volume of top dead center. So in the case of an Otto cycle, this is going to be the volume of V1 at bottom dead center, V2 top dead center. So that's just the reciprocal of R. So V2 is equal to VR1 over R. Okay. So in a similar fashion, I can write VR4 is equal to VR3, V4 over V3, and that's equal to R VR3. From previous lecture, we found that T2 over T1 would be equal to V1 over V2 to the k minus 1. And similarly, T4 over T3 would be equal to V3 over V4 to the k minus 1. And again, I can only do these sorts of ratios for isentropic processes. So this ratio here is then going to equal R to the k minus 1. And this one will equal R to the 1 over k minus 1. Only for a constant k. And recall that k is the ratio of Cp over Cv. And in the place of constant k, let's see, if constant k, specific heat ratio, then R is equal to V1 over V2, which is also equal to V4 over V3. All right. And eta, which, as we said before, was U4 minus U1 over U3 minus U2, that will become 1 minus Cv, T4 minus T1 over Cv, T3 minus T2. Which we can write as 1 minus T1 over T2 All right, so a little bit of algebraic manipulation there. And from before, from these two relations here, T2 over T1 and T4 over T3, the way that they make these relations for R and K T4 over T1 will be equal to T3 over T4. So I can write my efficiency, see if we can get it on the board here. Eta will be equal to 1 minus T1 over T2, which will be equal to 1 minus 1 over R to the k minus 1. All right, so these will be cold air standard only. Cold air standard only because everything down here, we assume they have constant specific heats or constant Ks. So what we see is that efficiency increases with increasing compression ratio. In my opinion, it's not important that you memorize all of these different relations, but if available to you, just know how to use them to find volumes or temperatures that you may not know.